So here next part of the discussion in polymers is in addition polymerization that is mode of polymerization in this mode of polymerization we have that is chain growth polymerization. We have chain growth polymerization, and the other one is that is step growth polymerization. Actually, in chain growth polymerization, it involves two types. One is free radical polymerization mechanism and cationic polymerization mechanism and step growth we can take, that is anionic polymerization. So to carry out this mode of polymerization, we need actually an alkene, comma chain initiator, it involves an alkene, chain initiator, chain propagator, initiator, propagator, and termination. So here if you take the first one, that is if you go for the free radical polymerization, in this let us start with free radical polymerization. If you go for free radical polymerization, we take a free radical in the presence of sunlight acting as catalyst, that is we can take benzoyl peroxide, take the benzene ring and attach the peroxide, this is benzoyl group with a peroxy bond, benzoyl peroxide, this is benzoyl peroxide, it has one peroxy bond. You can see the box here which I am trying to show. This is the peroxy bond, benzoyl peroxide in the presence of H mu. Let this be step 1, formation of free radical. So immediately homolytic fission takes place, the bond breaks symmetrically between the two oxygens of peroxy bond. So immediately you find that here you get benzoyl oxy free radical. We are going to get 2 molecules of benzoyl oxy free radical we are going to get. So you getting 2 free radicals. We call this as benzoyl oxy free radical. This benzoyl oxy free radical we can call it as chain initiator. We can call this as chain initiator. So here from the chain initiator reaction, take the benzoyl oxy free radical. This is benzoyl oxy free radical. Let it be, if this benzoyl oxy free radical, let it be given by R dot. So in step 2, that is chain propagation. If you take this R benzoyl oxy free radical it is treated with ethylene or ethene, it is going to give, that is RCH2 single bond CH2. Again you add one more ethylene molecule to this, you find that it is going to give RCH2 single bond CH2 single bond of CH2. So that means if you are going to add RCH2 taken thrice of CH2 with the free radical, if you are going to add n number of ethene molecules, then you find that here you are going to get, that is RCH2 taken thrice of CH2 single bond CH2 of n times, we should get the polymeric nature, and you find that here still it is a free radical, expanded form of the free radical. So if you go for step 3, in step 3 if you take, that is chain termination, if you take the chain termination, take the two free radicals, that is RCH2 taken thrice of CH2 single bond CH2, polyethylenic structure you have to take CH2, and again you add CH2 with an odd electron of CH2 single bond CH2 taken n times of CH2 taken thrice of R. You find that here the reaction goes for the completion and you get the terminated polymeric structure, RCH2 taken thrice of CH2 single bond CH2 taken n times of CH2 again. So the two odd electrons, they make up a bond formation here. So here you get CH2 of CH2 taken n times of CH2 taken thrice of R. So this is finally we got a polymeric product, chain elongated polymeric product, and this comes under the free radical polymerization with the chain growth polymerization. Okay, so here let us go to the second part of the discussion, that is mechanism. Let me put it in this way: mechanism of cationic polymerization. Mechanism of cationic polymerization. So here if you take like for the need of in step 1 for chain initiators, if you take chain initiators, if you can take the examples of Lewis acids. You can take Lewis acids like HF, H2SO4, AlCl3, SiCl4, etc. The best choice is take the sulfuric acid. In the sulfuric acid, in the chain initiating, in the step 1, that is take the sulfuric acid, H2SO4, upon dissociation it gives one proton and one bisulfate ion. So take this proton and you can just take the ethylene molecule or ethene molecule, and now you can add the proton. You are going to get a primary carbocation, CH3 single bond CH2. This is a primary carbocation. Take this primary carbocation and again you add one more number of molecules of CH2 double bond CH2. So you are going to get here CH3 single bond CH2 of CH2, that is 1 2 3. Yeah, here we are going to get, still it is primary carbocation, but you find that the number of carbon atoms have been increased in the straight chain pattern. Now for that, all this comes under the chain initiators. Then you can go for chain propagation, step 2. Take the chain propagation. In the chain propagation, CH3, CH2, CH2, single bond, CH2 plus primary carbocation, you add n number of molecules of ethylene or ethene molecules, you find that here CH3, CH2 taken twice, CH3, CH2 taken twice, or CH3, CH2 taken one times of CH2, CH2 single bond, polymeric, again CH2 single bond, CH2 plus. Still it is in the carbocation stage itself. Now go for step 3. In step 3, this is called chain termination. In the chain termination, immediately you take CH3, CH2, CH2 taken n times, CH2 ethylenic polymeric n times CH2. Now this CH2, which contains two hydrogens besides the carbocation carbon, the next carbon is taken as the alpha carbon. That carbon, it contains two hydrogens, so one of the hydrogen I am exposing with CH single bond CH and again CH2 with one positive charge retaining the carbocation. And now you can use bisulfate ion. Take the bisulfate ion, and here this bisulfate ion, between the CH and H, one of the bond will migrate towards the CH of CH2, and this proton gets separated by taking away the positive charge. So you are going to get here the final terminated product, CH3 single bond CH2, again CH2 single bond CH2 polymeric n times of CH double bond CH2 plus H2SO4. So we got an polymeric alkene, that is polyethene we got. And so therefore here it is very clearly understood that in cationic polymerization we have 3 steps. In step 1 it is called chain initiation, in step 2 it is called chain propagation, and in step 3 it is called chain termination, and finally we got a polymeric alkene. So this comes under the cationic polymerization. So here let us go to the third part of the discussion here, that is anionic polymerization. Anionic polymerization. In the anionic polymerization, it's a step growth polymerization. Point number 1. Point number 2, Lewis bases are chain initiators. These are the chain initiators. Example, you can take KNH2, K plus of potassiumide, if you take K plus of NH2 minus is acting as a base. So let this base be given by, that is B, a base with a non-bonding pair of electron. So here what is happening here is, if you go for the step 1, directly I am going to the step 1. In step 1 what I am doing is chain initiators. In this chain initiators you can take this base which contains a non-bonding pair of electron, and for this you add CH2. So the base will try to attack one of the methylene group of ethene molecule, so the pi bond electron will shift to the other carbon. So immediately you find a base with this non-bonding pair of electron, it forms a new covalent bond between CH2, and the negative charge is restored on another carbon. So again you can go for one more addition of ethylene molecule. So here you get one more extended chain, BCH2 single bond CH2 single bond CH2 of CH2 minus with a non-bonding pair of electron. Now take, this is chain initiator, go for chain propagator. go for the chain propagation. In the chain propagation, the base continues to bond with the hydrocarbon chain, CH2, CH2, again CH2 minus. Now add n number of molecules of styrene, 1 phenyl ethene you add, then immediately you are going to get one that is we can take here B, CH2, base attachment CH2, again you can take here, you can take CH2 of CH2 of CH of phenyl group with a bond taken n times. So this is how we can continue, and if you can, so this is where the polymeric, this is 1 phenyl, ethene, 1 phenyl ethene, otherwise called styrene. So this is the polymeric, this is where this is the polymeric extension, is observed here. And finally, in the chain termination, we'll see a new bond is formed for the polymeric extension. So here, if you look into the chain propagation, interestingly, here I'll just taken twice, and this is polymeric extension. And interestingly, for anionic polymerization, that is non-availability of chain termination step is not possible, or it is absent in the case of anionic polymerization. So in the anionic polymerization, we have only two steps. One is chain initiator step, and the other one is chain propagation step. In the chain propagation step, you can see the polymeric extension very clearly when you add the 1 phenyl ethene, that is styrene, to the already existing anionic intermediate. So this anionic intermediate, it accepts the polymeric styrene and it forms the continuity of the extension of the chain in the form of polymeric extension, and finally we got the final product. And you can see that in the product there is no certain charge, that is negative charge. So therefore we have completed all the three modes of polymerization, that is cationic polymerization, free radical polymerization, and also anionic polymerization. So the next part of the discussion, that is the last part in the polymers, that is biodegradable polymers. So here these are nothing but biodegradable polymers, are nothing but these are aliphatic polyesters. This may be aliphatic polyesters, or this may be aliphatic polyamides. These biodegradable polymers, they readily biodegrade. They readily biodegrade through enzymatic oxidation or hydrolysis. Enzymatic oxidation or hydrolysis. Some of the best examples of biodegradable polymers are, that is, we can take PBHV is one of the most sought after example of biodegradable polymer. Then you can take PGA, then PLA, and you can also take nylon 2, nylon 6. So these are the four important biodegradable polymers. If you go for PBHV, this is poly beta hydroxybutyrate, poly beta hydroxybutyrate co beta hydroxyvalerate. This PBHV is the one of the most sought after biodegradable polymer. It is also called that is capsule polymer. Capsule polymer. It is also used in that is orthopedic drug. It is used in orthopedic packing of drug. This PBHV, when we consume it in the form of capsule, this capsule readily it dissolves in our stomach, and it tries to give the necessary action at the necessary areas wherever it is supposed to function. And PBHV, that's why sometimes it is also called as capsule drug. Then if you go for PGA, it is called polyglycolic acid, PLA, polylactic acid, and this nylon 2 and nylon 6 also, it's a biodegradable polymer. But here we take alpha amino acid, NH2 single bond CH2 COOH, and we have that is NH2 caproic acid, NH2 CH2 taken 5 times of COOH. This is alpha amino caproic. Together, when you condense these two amino acids together, we get the nylon 2 and nylon 6 biodegradable polymer. So now let us see how best we can prepare, that is PBHV. If you go for PBHV, if you're going for PBHV, it is made up of two different, it's a copolymer, and it undergoes condensation polymerization, and because we are saying that poly beta hydroxy butyrate, so what I'm going to do is I'm going to take one carboxylic acid, and here at the alpha position, this is CH2, CH of OH of CH3. This is beta hydroxy. So this is alpha and this is beta. So this is beta hydroxy butanoic acid, This is one polymer, and the other one is CH3, CH2, CH of CH 1, 2, 3, 4, 5. 1, 2, 3. Okay, we call it as poly beta hydroxy valerate. Beta hydroxy means this is alpha and this is beta. So here I am going to place one OH group, and this is CH2. So this is beta hydroxy valerate. This compound is beta hydroxy valerate, and this compound is beta hydroxy butyrate. Both of these undergoes, that is condensation polymerization, that is PBHV. So let us see how we can prepare PBHV through condensation polymerization. Let us write the necessary equation. So now let us go for the PBHV. Number one, first one, PBHV, biodegradable polymer. We take two monomers, that is we can take carboxylic acid with the CH2, again CH2 CH of OH of CH of OH of CH2 of CH3, n number of molecules. Again you add OH of CH of CH2 CH3 CH2 of carbon double bond of OH, n number of molecules. So here, mind you, we are taking n number of molecules and we are subjecting it to polymerization, because this is a carboxylic acid. So from here we are removing the proton, and again this is a carboxylic acid, I am removing one more proton and one alcohol from here. So therefore you get a polymeric product in this manner, that is CH of bond extension CH2 CH3, again CH2 of carbon double bond oxygen, again O of CH of CH2 of CH3 of CH2 of carbon double bond oxygen O, and here a bond extension, and this is base N. So here what is interesting here is this is beta hydroxy, butanoic acid, which gives stiffness to the polymer, and this is beta hydroxy valerate, which gives flexibility to the polymer. So the capsule polymer contains two important characteristic features, stiffness and flexibility. Stiffness is offered by beta hydroxy butanoic acid, and flexibility is offered by beta hydroxy valerate. And when these two are participating in the polymerization, of course minus n number of water molecules have to be eliminated because it's a condensation polymer. Two different monomers are involved, and you can see the aliphatic polyester. So we call this as, this is nothing but polybeta hydroxy butyrate co beta hydroxy valerate, and here you are finding that this is the ester linkage. We can find that this is the area where you can offer the ester linkage. In fact, this is the area where you can highlight. So here we can see the ester linkage. This is the aliphatic ester linkage. You can see CH2 carbonyl group, again O CH of CH2 CO, OCH of CH2 CH3, and again CH2. This is esteric linkage. So we can just call them as poly esteric in nature. So this is one of the important aspects which you have to keep it in your mind for the PBHV drug, biodegradable polymer. So second one, if you go for PGA monomer involved is glycolic acid. Monomer involved is glycolic acid, and in this glycolic acid you can take one primary alcohol and one carboxylic group. This is the glycolic acid, which is optically inactive, and because only one type of monomer is involved, we can say that this is going to form a homopolymer. So therefore now if you want to see that the glycolic acid is participating in the that is the polymerization, CH2OH primary alcohol, carboxylic acid, again OH plus again OH of CH2 of carboxylic acid, again OH, n number of molecules. If it participates in the polymerization, we can find that here one OH group is removed out, and here one molecule of water is removed out, and here again one molecule of water, minus 2n number of water molecules are removed, and you are going to get the polymeric structure in this manner, that is one carboxylic group O of CH2. Again you can find a ester linkage with a carbonyl group, again O of base N. This we can call it as polyglycolic acid, PGA. This is polyglycolic acid. Next one, that is the third one, if you take, that is PLA. This is polylactic acid. Monomer is lactic acid. Lactic acid structure you can take, that is CH2OH, CH2OH of CH of CH3 of carboxylic acid. Yes, it contains a symmetric carbon. It is chiral in nature and it is optically active. So take this lactic acid as a monomer. N number of molecules you take, that is OH of CH2 of CH of CH3, again carboxylic acid, OH plus, again OH of CH2, CH of CH3, again carboxylic acid with one OH. So you get over here. So this is carboxylic acid, so remove your one molecule of water. This is primary alcohol, so you remove one molecule of hydrogen, alcohol, so you can remove the oxygen along with the hydrogen, and here the carboxylic acid minus 2n number of water molecules, and you get the final product as, that is, take the CH2 group, single bond, CH, CH3, again carbon double bond oxygen, oxygen, again CH2, CH of CH3, carbon double bond oxygen of, taken n times. So this is polylactic acid, and this is shown as the esteric linkage, something like an esteric linkage. So therefore this lactic acid, aliphatic polyesteric in nature. So this is how we can prepare the PLA. And the last one, we can go for the last one, that is nylon 2 and nylon 6 also we are going to finish off. And this is something about the polylactic acid. So the last part of the biodegradable polymer, that is nylon 2, nylon 6. If you take, it's a biodegradable polymer, it's a biodegradable polymer, it's a copolymer. If it is a copolymer, then it contains NH2 single bond, CH2 of COOH. This is alpha amino acid, that is glycine. Then and you can also take NH2 CH2 taken 5 times of COOH. This is amino caproic acid. It's a condensation polymer. And also step growth polymer. So here if you take the take the two monomers, H of NH single bond of CH2, carbon double bond oxygen of OH plus plus again H of NH of CH2 taken 5 times of carboxylic acid of OH. If you take n number of molecules, then we can get here remove one molecule of hydrogen, one hydrogen atom, and remove one OH group from the carboxylic group, and here one OH group from the carboxylic group. So you get over here, that is NH CH2 carbon double bond oxygen, NH again CH2 taken 5 times of carbonyl group, base in times of. So this is a polyamide of, that is nylon 2 nylon 6, because here we have 6 carbons, 5 methylene groups and 1 carbonyl group, 1 methylene group and 1 carbonyl group. That's why we can call it as the nylon 2 and nylon 6, and this is the amide linkage. So this is going to become the amide linkage, also called peptide bond. So this comes under the nylon 2 and nylon 6 biodegradable polymer.